Greetings, folks. My name is John Gabriel, and this is the New Calculus channel. And today I'm going to be discussing, once again, a very important topic. Something went in my eye again. And the topic is about the abstract unit, okay? And what is the difference between the geometric unit and the algebraic unit? Both are abstract. But let's see what is the difference. So let's begin. Now, there are many ideas of what is a unit, but none of them correctly capture the meaning of unit. This is hardly surprising because one can't possess anything but a superficial understanding without realizing the concept of ratio. Why? Because ratio came long before the concept of unit and number itself. Now, in my very well written article, and you all know how much I hate writing, at this link here, which I shall place a link to this article in the details section, I discuss the complete realization of number from nothing, as it actually happened to my ancestors over 2,500 years ago. So before continuing, you should probably study this world-class article. It's only 8 pages, and it shouldn't take you too long. Do not think that you can simply read through it in just a few minutes. That's not possible. It requires a lot of thought. So I encourage you to read it first and then come back to the video and continue to follow the information that I'm about to share with you now. So there is no such thing as a standard unit in geometry, okay, because there is no ideal unit. Now here's another link that you'll find to a YouTube video in which an Australian professor produced a video about Euclid's big problem. By the way, it turns out that Euclid isn't the one with the big problem, but rather she is the one with the big problem, because she doesn't understand the difference between a geometric unit, a geometric abstract unit, and an algebraic abstract unit. And this is what I'm going to illustrate to you by means of 2 well-known examples. So, in the top of this image, you'll see 2 squares, okay? Obviously, the sides of a square are all equal. And if you try to measure this red diagonal with any of the sides, you will realize a magnitude that has no measure. That magnitude, as you all well know, is called the square root of 2. It's not a number, it's a magnitude. And by the way, it's not a coincidence that Euclid talked about the word magnitude, which in Greek is megathos, in book 5, long before he got to book 7, in which he discusses the unit, okay? And then derives the theory of numbers. So now, do you see, if you take any other square and you measure the red diagonal, you will again realize the concept of square root 2. It doesn't matter what square you use. So what does this tell you? What is the meaning of this? It means that in geometry, there is no ideal unit, okay? Because really what you're doing when you realize the diagonal is you're using one of the sides as the unit. So it tells you that the size of the unit does not matter when you realize square root 2, okay? And that is really also what happens in algebra. In algebra, you really have a generalization of the geometric unit. Okay, it's a generalization. So in geometry, for example, you can take any circle and use its diameter in an attempt to measure the circumference of the circle. It doesn't matter which circle you use, you'll realize that the approximate measure each time is 3, or 3.14159, or more digit if you decide to use one of the power series or whatever other formula you might have. So that's not important. The important thing to remember, however, is that there is no unit that measures either the diagonal which is the hypotenuse of this right-angled triangle, isosceles right-angled triangle, or any diameter that measures the circumference. In other words, both these magnitudes, not numbers, because a magnitude is not a number and a number is not a magnitude, okay? Both of these have no measure and are called incommensurable magnitudes. And of course, if any serious mathematician, serious math student studied the elements, they would see that the ancient Greeks knew about these incommensurable magnitudes, which they interpret incorrectly as irrational numbers. Okay? An incommensurable magnitude is not an irrational number. It's not a number of any kind. It's a magnitude that has no distance. Okay? In Greek, we say alogos arithmos, okay, which means an absurd number. Okay? So there, in other words, it's not a number. So from the previous slide, we learned that the choice of the unit does not matter. Any size unit will produce the same measure. By the way, the word measure, which is metro or metron or metrici, appears in the elements countless number of times, because everything that is done in the first 6 chapters is laying the foundations for the definition of number. Now, granted, Euclid didn't do a great job of defining the unit, because he said in Greek that roughly that a unit is that by virtue of which all things are one. Now, if you want to really understand, you should read my article, because I get it right. I explain to you exactly what is a unit. So both the geometric excuse me, and the algebraic unit are abstract, but in geometry, any chosen unit measure is always exact. And arithmetic with any distance in geometry produces exact results. You can multiply, divide, add, subtract, and you will have the precise result. There is no approximate measure as in square root 2 or pi in algebra, because what happens in algebra is that we have a generalization of the geometric unit. So let's look at a simpler example here. So I've taken 2 lines and divided them into equal segments. Now in geometry, the measure of these lines is completely different. The top line here, the longer line, is evidently much longer than the shorter line, okay? And if we wanted to find the difference, we would simply overlay the longer line by the shorter line, and that would tell us exactly in geometry the difference. And similarly, to find the sum of these 2 lines, we would use requirement 2, which says any straight line can be extended indefinitely, and thus it doesn't matter what the measure of this line segment is or how long, this line here can be extended by this much. And so we have a sum. But of course, realize that difference is the most primitive arithmetic operator. And also take note that all the operations that you find in arithmetic and in algebra come directly from geometry, okay? So for example, in geometry, you can use equal angles subtended on the same arc to find a product or a quotient. And I'm not going to go into that because I've already done that in another video. So what I'm going to focus on now is Webster's definition, which is absolute garbage and doesn't explain the meaning of unit or the abstract unit. Either phrase really remains very vague even after reading this. So for example, this definition here, which says the unit of numeration 1 taken in the abstract, or the number represented by 1, or something concrete or determinate or determinate unit, is garbage. In fact, none of this here tells you what is a unit. It doesn't even explain what is a unit, never mind an abstract unit. So to talk about the unit of numeration is also somewhat circular, because the unit is a number, okay? And also a unit of measure such as a foot refers to a physical measure, which is neither geometric nor algebraic, okay? That should be nor algebraic, by the way, not geometric or. So where the size of the chosen unit indeed matters, the only time the size of the chosen unit matters is in physical measurement. Otherwise, the size is irrelevant. We deal in mathematics only with the abstract unit, okay? Not the geometric unit, the abstract unit, which is derived from the ideas of the geometric unit. So to be a number means to have a name assigned to a given measure that describes a magnitude or size. Mainstream mathematics academics have never understood the concept of number. In fact, they don't even have a clue what the meaning is of number that is descriptive for any given number, okay? So in the next video, I'm going to discuss Richard Dedekin's comical essay, which is called, I think it was an essay on numbers, and I'm going to focus on this chapter here, which is continuity and irrational numbers. Since I don't have any time to discuss it, I'll place it in another video. But in the meantime, if you're not already a subscriber, become a subscriber, spread the news of this wonderful channel where I'm sharing never revealed before secrets with you and helping you to understand the most important concepts of mathematics, of which number is the most important concept. You know, and you'll see in the next video why number is the most important concept from what I'm going to explain to you therein. So I'm going to leave you with this now, and thanks for watching my channel. Thanks for being a subscriber, and I value well thought out comments or questions. I have no time for fools. So please, if you're going to be in an argumentative mood, spare yourself. I'm not even going to publish a comment. I'll just ban you. You won't be able to comment again. And that will be the end of it. So this is the New Calculus channel. My name is John Gabriel. Till next time, goodbye.